Okay, so if entropy exists, then we can start to consider the second law of thermodynamics. Because depending on how you read this, if you read the second law of thermodynamics as written by a physicist, you just scratch your head and say, I don't know what that means. Chemists write it a little bit more meaningful, and the same way that the first law says something really contrived, in a cyclic system energy is conserved. Okay, what does that mean? It means energy cannot be created nor can it be destroyed. Oh, I understand that now. In a way that you can understand, the second law of thermodynamics is basically saying this. What it says in reality is along the lines of, if you account for all the motion of heat moving from an initial state to a final state, then the difference in that heat has to be accounted for by some change in entropy. So, or the entropy in the universe, and the universe just means the thing that you're looking directly at, and then everything outside the beaker, which will come back to bite us in a minute, because that number's really hidden. So if a reaction is spontaneous, it means it's primed to go in a way that doesn't require any external help. It's like it's rolling downhill, and therefore its entropy is always going to be a positive number. And that will contribute to the entropy in the entire universe. Okay, so the entropy in the universe always increases for a spontaneous process. All right. Now we have and let me just tell you what that means. So the universe equals our reaction, or if it's a process, plus its surroundings. One of the things that, and it's not part of the law, but we'll get back to, is, I gotta do this. I'll come back to that. Okay. I'm going to write this down and then fact check what it is that I'm saying. But standard entropies are listed in Appendix C of the book. I believe that's the appendix that I printed and tagged on to the end of problem set 3. Yep. So in Appendix C, which you might have printed out or you've got in the book in front of you, it'll give you the name of a compound and then there are three columns. And the first column is the enthalpy of formation, which again is not an enthalpy. That's an enthalpy change. But enthalpy change of formation gets a bit tiring to say if you have to say it 100 times a day. So we call that enthalpy of formation, standard enthalpy of formation. And then followed by a number we don't know yet called delta G. And then followed by entropy, standard entropy. And I might come back to that table, so I'll mark it. So the standard entropies are listed in Appendix C, and they are given symbol S, and then raised to the power, superscripted, not raised to the power, superscripted 0. Sometimes that's got a line through it, sometimes it's got a line through it that way. Mostly nowadays it's just a 0. If a value is standard, what exactly does that mean? So the last time that we saw it was enthalpies of formation. That some values of enthalpy change were quoted as being standard. What did that mean? The standard conditions, recorded at standard conditions. And what are standard conditions? One atmosphere and 298 Kelvin. So basically room temperature and atmospheric pressure. So this means 1 atmosphere and 298 Kelvin. So if I look at standard enthalpies, and remember we can figure out a reaction's overall enthalpy by just summing the enthalpies of formation of all the bits and pieces in it. We can do the same for the entropy. And they're quoted, but they're quoted not as changes, but as actual numbers. Okay. Just write what I've got in my book. That's not a particularly good example. Maybe I've got a better one to follow. Oh, yes, I do. Yeah. So if I look at this reaction, I take some hydrogen, that's a gas, and take some chlorine, that's a gas. Both of these are diatomic homonuclear molecules, and I mix them together. Hydrogen is in group 1, can only make one bond. Chlorine is in group 7, can only make one bond. No reason that they cannot make a bond to each other. So it's possible that I scramble that. And we're not talking equilibrium anymore. Let's make that an arrow. We will ultimately come back and talk about equilibrium. All right, so if I look in Appendix C, I find that the standard entropy for hydrogen is 131. And the standard entropy for chlorine is 223. And then the standard entropy chloride is 187. Just check those numbers. Oh, where would I find HCl? Is it going to be under the Cl? Yeah.
How do they determine the values for that?
I'm not entirely certain. So you have to know, well, we can do it in isolation. I wouldn't know how you would find the number on its own, but the entropy is a missing number. Okay, so the entropy is the missing number that describes enthalpy being, well, that's the big heat change when a process works, when I go from this place to that place. Now, if I can account for everything that's supposed to happen, and that number is missing in the enthalpy change, then the only place that it is, that it comes out to be, is here. So experimentally, that's probably the way that they do it, but in isolation, I have no idea. So the entropy, depending on which, let me read you the physics definition. Okay. In a natural thermodynamics process, the sum of entropies of the interacting thermodynamic systems increases equivalently. Perpetual motions of the second kind that spontaneously convert thermal energy into mechanical work are impossible. So there is a number that is missing. That second law of thermodynamics indicates the irreversibility of natural processes, and in many cases the tendency of natural processes to lead towards spatial homogeneity of matter and energy, and especially of temperature. It can be formulated in a variety of interesting ways. It implies the existence of a missing quantity called entropy, and in terms that implies that two initially isolated systems in separate but nearby areas of space, blah, 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 blah. Physicists wrote this. But it says that this implies that there is a missing number in your calculation. Okay. So if we do things where you measure work, which when we look in textbooks, there's always a section right before enthalpy where it says, oh, this is a closed system and this is a state function, and therefore we have to consider the amount of work that's being put in. We never ever do any of those calculations. They may have been done 100 years ago, but nobody's repeating them now. So this is the missing number that's missing out of the enthalpy change. And its units are in joules, not kilojoules, per Kelvin, per mole. I think kind of recently, we're starting to move that K to the back. And I think the reason is that a K and a J, both capitalized next to each other, sort of reads like a kilojoule. And it's not. It's 1,000 times smaller than an enthalpy. Entropy numbers are this little number that's in the process, but not immediately visible to us. So I think this is nicer. Joules per mole per Kelvin. Okay, that's our process. We've done this before, but never for entropy, we did it for enthalpy before, where if you want to know the change of entropy for this reaction, what you do is, what does that symbol mean? That's the sum. Sigma, capital sigma, means the sum of the number of moles of the entropies of the product minus all the sum of the moles of the standard enthalpies of the reactants. We did something very, very similar when we calculated the enthalpy change for a reaction from quoted formation enthalpies of formation that were in the appendix. Okay, just slot the number in. So product is all the sum of, just add them up, this just means add the numbers together by how many you've got of the entropy changes, standard entropies of the product. So I've got 2 times 187 minus 131 plus 223. Seven times 2. Don't know if I've got it written down. I probably do. No, I don't. Do you have a number?
For 2 times 187?
Oh, we can do it the long way around. Yeah, go ahead and do that.
374.
374. And the 131 plus 223?
354.
354. And 374 minus 354 equals? 20. At this point, the same way that we wrote it for enthalpy changes, I'm going to write a positive in there. Don't need it, but I'm going to write it in anyway. And then my joules per Kelvin, depends what you're looking at. I'm going to write the per mole in here. Usually when you write for a reaction, the same way that we did for enthalpies, I wrote it in and I took it out again. The individual numbers are joules per Kelvin per mole, but I said before, it depends what you're looking at. If you're trying to consider it from this point of view or from that point of view, you might have a different idea of what per mole means. So for a reaction, drop the per mole and just give me joules per Kelvin. Okay? Reactions don't need it. And we did that before with enthalpy changes. When we look at an enthalpy change of formation for an individual molecule, we quote it in kilojoules per mole. But then when we write that all out as a reaction, just give me the kilojoules. That the reaction either gives out or takes in this many kilojoules. You don't have to tell me per mole, because you don't know if I'm thinking about, it's the reaction as written. We don't know whether I'm thinking about number of moles of product and you were thinking about number of moles of reactant. Okay, so don't put it in. It's only going to get more confusing. All right, that's a positive value. It's really, really small. It's a small value, 20 joules. We've been seeing enthalpies of 20,000 joules. So this is a small number, but it is positive. And so that's going to direct that this is going to favor that reaction being spontaneous. In the direction shown, guess what would happen if the value came out that it was negative? It would mean that the reaction was probably more likely to happen the other way. So this tells me in the direction shown. And I have really hedged my bet with my statement. I have said favors, not is, because we haven't got there yet. There's a bit more going on in the world than this. The thing that's real, I mean, enthalpies are going to be significantly larger than this. This is a small value that's going to explain the missing link, right? This is the small number that explains, well, how come endothermic reactions work then? Endothermic reactions are supposed to require heat being put in, they're supposed to be difficult, and yet I see them happening. Well, entropy says it's okay, that this number balances out what's going on. So the delta S value is positive, tells me, and small, but it's very, very small. Let me see if I've got another one. I did say when I looked at this, that's not a particularly good example. Let me show you the other way around. If I take a nitrogen, it's a gas, and 3 hydrogens, it's a gas. Now we saw this in the previous chapters a couple of times, and we know that that's an equilibrium reaction. But that's outside of the scope of this chapter right now. We're going to come back and fix it for equilibria later. I'm going to put in my values of standard enthalpy, and it turns out that this is 193 joules per mole per Kelvin, and this is 192. And that's 131. Okay, so from the appendix. And then I can find that the entropy change standard for this reaction, again, is the standard entropies of the product minus the standard entropies of the reactant. My product, 2 molecules of ammonia, 193. And then I have a 192 plus 2 times 131.
Should it be 3 times 131?
Oh. Yep. Yes, it should. Okay. 2 products, and they're one of those, and 3 of those, so they all add up. And I should, this term right here is going to be significantly larger than that term. So my number's not going to be positive. It's going to be a negative number. And it's negative to the value of, yeah, 199. And again, we're only, because we're talking about a reaction, I'm not going to write the per mole in there, joules per Kelvin. Okay, so let's talk about that. That's a much bigger number and negative. That negative value means unlikely to be spontaneous. In the direction shown. Now, there is something that would have helped us predict that. We saw this earlier. We had seen this previously when we converted KCs to KPs. The KP was KC plus the RT raised to the power of the delta N. Delta N is going to be the difference in gas molecules between the right-hand side and the left-hand side. Here I have 1 gas molecule plus 3 gas molecules. And over here, I have 2 gas molecules. Now, what was special about the entropy of gases? Gases have high entropy. So, just looking at this reaction, the universe does not want this reaction. It doesn't want it. Because you're turning 4 gas moles with all of that entropy into 2 gas moles. That's less entropy. That's more order, less disorder. That's not what the universe wants. The universe wants to smash everything to pieces and leave it all in dust. This is creating order out of disorder, and in turn, the universe is going to say, I will let you do this reaction, only if you give me energy. So, if this reaction turns out to be endothermic and pointing the wrong way in terms of entropy, I'm going to have to pump a lot of energy into this reaction. Now, if it turns out to be exothermic, then maybe 200 joules pointing in the wrong way doesn't matter. If this reaction is exothermic to the, let's say to the amount of 1 kilojoule, that's 1,000 joules, then having 200 joules pointing in the wrong direction isn't going to matter, because the enthalpy will just trample this and say, yeah, I know that we're pointing in the wrong direction, but the products are so much lower in energy that we're just going to go for it. Which brings us to the point of, we've talked about enthalpy. It's time to start factoring it in. And the first way that we factor it in is the curious way. That you might have to consider what's going on in the universe around the container. So, I have a beaker. And the beaker is currently performing a reaction in which A is being converted into B. All right. A going into B, I can't really say anything about that because I have one reactant and one product. So the number of reactants and number of products is the same, therefore I don't know that the universe has anything to say about entropy here. If I changed it, the two A's are turning into B, then I am ordering the universe. I'm decreasing the amount of disorder in the universe. This reaction is going to have a negative value of entropy. Oops, this reaction is facing the wrong way. It will not, entropy says it's probably not going to happen in the direction that you're pointing at. Because if I move the 2 here, I took one A and made it into 2 B's, then hey, I'm looking at something that's good. So right now, my entropy should be less than 0. But what if this reaction also has a delta H that is also less than 0? What does that mean? If my delta H is less than 0.
It's exothermic.
It's exothermic. Heat is given out. Where does the heat go?
Surroundings.
Okay, what's in my surroundings? What's in the surroundings? That is a beaker on a tabletop in this room at standard conditions. 298 and 1 atmosphere. What is outside of the beaker? It's 78% nitrogen and 21% oxygen and 0.1% argon. Okay. When heat is given out, where does the heat go? gas molecules pick it up. And what happens when gas molecules increase in thermal energy? Remember that? Going to this. With a value here being, that's the insane speed that's strong enough to actually do something chemical. Okay, so the heat that comes out of the container has to go somewhere. It's going to heat up the gas molecules that are around it, and then they're going to shoot off high energy. In fact, you will get eddy currents of heat moving around the container. What just happened to the entropy of the universe? Yeah. So your reaction itself is not entropically favorable. However, the enthalpy change for this reaction pumps out heat which changes the enthalpy of the surroundings of the container, and the total entropy change is the entropy change for your reaction plus the entropy change of your surroundings. If it's possible that the enthalpy contributes enough heat to make the entropy of your surroundings now be significantly large and positive enough to overcome the fact that you didn't have it inside this reaction, then now your reaction will go. And I've got some numbers for that, and it's here, I think. So if we look at that reaction again, we find that the enthalpy change for nitrogen plus 3 hydrogens combining to make 2 ammonia is negative. That's an exothermic reaction. 92.6 kilojoules. That's 92,000 joules of energy versus 200 pointing in the wrong direction. So that 92,000 joules of enthalpy change could have an effect on the surroundings, not on what's in the container, not on the reaction, but on the surroundings of the container that is enough to let this reaction go. So that's the enthalpy change of my reaction. Sometimes we say reaction and surroundings. Other times, because it's a process, we'll say system. Don't know which way the book says it. Let me look at what the book says. System and surroundings. Because it isn't all reactions. Sometimes it's things like take a gas, squeeze that gas down to a new pressure. And anybody that's ever inflated the tires on their car knows that when you squeeze gas into a smaller volume, that heats up. Okay, so have to take that into account. Now that temperature change gets accounted this way. That the enthalpy change for the surroundings is the enthalpy change of the, I'm going to call it the system. It's the whole thing. Let's call it reaction. Right here. So the enthalpy change of the entropy change of my surroundings turns out to be equal to the enthalpy change of the reaction divided by its temperature. And then we're going to turn negative values. Because a negative value for enthalpy means favorable, right? Negative value for enthalpy, favorable. Giving my energy away, that sounds like a good thing. Positive value for entropy is favorable. So this negative needs to go in there to change the sign of the enthalpy to match what I want for my entropy. So here we go. That could be the negative of negative 92,600 joules divided by 298 Kelvin, which is going to give me a number in joules per Kelvin. Because we did this at standard temperature, my temperature right here is 298, those numbers can stay as standards. And for the value of my surrounding entropy change is equal to, would you look at that, plus 311. Back to here, you can write this as a new line under yours. The total entropy change is my negative 199 plus 311 equals, that's a positive value. So 112. 112 joules per Kelvin. Which means that my reaction, which is unfavored by the number of moles in the gas phases between my reactants and the products, as written, looks like a terrible reaction, but it's so exothermic that it disrupts the surroundings. And turns out to be spontaneous in the direction shown. Now, if only there was a way to do all of that calculation but put it in one thing. It turns out that there is. Because this enthalpy change in the surroundings is just this term. And all of those values are in the appendix. All of these values, standard enthalpies, they're all in Appendix C. And all of those values, they're in Appendix C as well. So any reaction that I write down, as long as I know what the value of the temperature is, all of my numbers now exist. So I'm just going to rewrite all of that into one equation. And this is where we will come back and finish. Oh, are you still writing that? Tomorrow, because this is where the big utility lies, and we've got some really nice questions because all the data are in the appendix. We are going to invent a name, a value, called Gibbs free energy. Apparently it's not possessive. It is not Gibb apostrophe S. It's Gibbs free energy. And that value is given symbol delta G. And delta G is equal to delta H minus T delta S. And that is for any reaction at any temperature under any conditions. Which is great if you want to go and measure stuff. However, if you just want to figure stuff out by looking at standard conditions, what are standard conditions? 1 atmosphere and 298 delta G standard equals delta H standard minus T, which is going to be 298 delta S standard. And that's actually going to allow us to vary the value of T a little bit, because all the other numbers are all going to work. So standard conditions, this now is true. Okay, let's look at what we want. We want delta H for a reaction. Here are your two scenarios. Exothermic. You start with a reactant that's high in energy, and you end up with a product that's low in energy. Does that sound like a good deal? Or do you think that nature wants to go the other way? Think that nature wants to start with molecules that are low in energy and then build them into products that are high in energy. Does that sound reasonable? No. This is what nature wants. It wants to stabilize stuff, to turn their energy low. So we're going to want reactions that are exothermic. The more exothermic you are, the more likely that you're going to be favored by the universe. So we're looking for numbers that are big and negative. And then, entropy. We want our entropy changes to be positive. We want the disorder in the universe to increase as our reactions proceed. So we want this value to be positive. But that number, the delta S, is going to be in joules per Kelvin, whereas this one is in kilojoules. So But this one's always going to be 1,000 times bigger than that. Always, not true. Often going to be significantly larger than that one. However, I have a T right here, and the T is in Kelvin. So that number could be hundreds of Kelvin in magnitude. So it's going to multiply this term. There are three possible answers here. The delta G is larger than 0. It's a positive value. Or that delta G equals 0, or delta G is less than 0. Here are my two terms. Oof, running out of ink. My two terms are this. I have the delta H that I want to be negative. And then I have the T delta S that is going to be a small number, delta S, small positive number, multiplied by a bigger positive number, but then overall having a negative effect because I'm just subtracting from it. So if the entropy is favorable, it's a positive number, and the enthalpy is favorable, is a negative number, then delta G gets to be negative. And when delta G is negative, what that means is that my reaction is guaranteed to be spontaneous in the direction that I've shown. So I want values of this made-up number, delta G, for Gibbs free energy change, to be negative. The more negative they are, the more likely my reactants are speeding towards being products. Could be 0. What happens at 0? Let's skip 0 because that's difficult. What happens at the wrong value? If I have a positive value, could be that my reaction is endothermic, or that my disorder is facing the wrong way, and then when you multiply it, it doesn't come out right. So these reactions will be spontaneous in the reverse direction. Okay? So what does that mean for delta G equals 0? Delta G equals 0 means not going forwards and not going backwards. Your reaction's at equilibrium. Okay? We're going to have all the fun in this chapter with delta G. Yes, the S is great. Yes, the delta H is great, but it all gets explained by delta G. Okay. We're done. I will see you at 1.